And okay, hi everyone. Today we are going to present on the topic passive suspension system. So I am Vishal Jain. So what is passive suspension system? In this, it contains a spring and a damper attached to the wheels. So what is the function of the spring? As everyone knows, it provides supports to the body of the car and also to observe and store vibration energy. So in designing process, as everyone knows, stiffness of the spring is calculated. Shock absorber. What is shock absorber? So it dissipates the vibration energy stored in the spring and controls the input from the road that is transmitted to the vehicle. So damping action, if you see, that is nothing but coefficient of damping. Here it is selected at the design stage and for type of vehicle performs required for ride or the comfort or the handling. So second is like it varies from vehicle to vehicle as requirements are changed. So the passive suspension system, it actually acts as an open control loop system. As everyone knows what is an open loop. If its design has high damping or too hard suspension, it will transfer most of the road input or throwing the vehicle on irregularities of the road. So here, before going into mathematical models, we know here using these models, the analysis, design and synthesis of complex physical system can be simplified. So the definition here goes like, the mathematical description of the dynamic characteristics of a physical model is called a mathematical model. So a given physical system would have different mathematical models depending upon the variables considered and also the coordinate systems chosen. So here is the division of vehicle suspension models. This is one is a quarter car model, half car and full car. Under half car there are two subdivisions, roll degree of freedom and pitch degree of freedom. So we will now go in depth of quarter car model. So quarter car model, it represents the suspension system of a quarter of the vehicle, that is the one wheel of the vehicle. So the vehicle here is connected to the road via a linear spring and the damper in parallel, which represents the primary suspension, which is in series, and it represents the vertical stiffness of the tire of the vehicle. It also consists of two masses, one is unsprung mass and sprung mass. The vehicle body, as you can see from the diagram, the vehicle body is represented by using the sprung mass, which is ms, and while the mass due to axle and tire are represented by unsprung mass. So here from the diagram you can see ms is the sprung mass, mu is the unsprung mass, ks is the spring stiffness, kt is the tire stiffness, and ds is the damping coefficient for suspension. So what are the assumptions made in the quarter car model? These are the 5 assumptions that are made. This is the tire is modeled as a linear spring without damping. The second is the behavior of a spring and the damper are linear. There is no rotational motion in the wheel and the body, and the effect of friction is negligible, which is important. So next comes a half car suspension. Here it is a 4 degree of freedom system. The sprung mass is considered to be half here and both halves are considered independent. So here it can be classified as two types, roll degree and pitch degree, as I explained in the previous slide. So here the roll degree is considered to be half at the rolling axis of the car, where the disturbance or the shock is acting at the left wheel of the front axle, and on the right wheel of the front axle is also considered. Here and then the pitch degree of freedom, where pitching axis is the point of separation. The half car model is actually just used to analyze the dynamic response of the car in case of road irregularities at random. Now going into full car suspension, here the popularity is increasing in automobile industry nowadays. Here this is 7 degree of freedom, as half car was 4 degree of freedom system. The 7 degree of freedom system, they are the heave, reach and roll of the vehicle body and the vertical motion of each of the 4 unsprung mass. These systems are highly flexible, which allows them to be specifically tuned for performance. Here is the diagram for full car suspension model, and here is the half car suspension model.
Now coming to the bar diagram of mathematical modeling of quarter car suspension system, as my friend Vishal said that quarter car suspension model consists of 2 degrees of freedom. It consists of two masses, sprung mass and unsprung mass. This is the field bar diagram of unsprung mass. This is the stiffness coefficients of Kt and Ks, that is acting opposite to the force that is exerted by the tire. And Kt is the tire coefficient of stiffness and Ps is the damping of suspension. And this is the sprung mass. This is the sprung mass. The forces will be acting on sprung mass will be opposite to the unsprung mass, so that the coefficient of stiffness and the damping will be acting in opposite direction. This is the actual quarter model suspension diagram that is exerted by a single car wheel. As you saw, they have combined both unsprung mass and sprung mass. This is the equation of motion. It is done by Newton's second law. As I said that it consists of both sprung mass and unsprung mass. This is the first equation is used for only unsprung mass, and second equation is done by sprung mass. Here what we done is mu is equal to mz double dot of u, means differentiation of z twice, and for damping it will be only one time of differentiation, so that we will obtain two for unsprung mass and sprung mass. So to convert these two equations into matrix form, we have to make into different types of matrix. One is damping matrix, stiffness matrix, and coefficient of mass.
Next.
This is the combined equation of second order matrix, which will be combined just only for matrix of mass and damper and stiffness. So that we have to obtain these x double dot of x and x of x and x dot of x and x of x. To calculate this type of equations, we have to use three types of models. One is state space model, transfer function, and Laplace transform. Let's talk about individually. This is the state space model. Here it consists of input, output, and the state variables. The state variables is in the order of matrix form, and the differential equation is in the order of matrix. State space model consists of a minimum number of state variables, which is equal to the differential equation of CM. Because in quadrant model there is 2 degrees of freedom, so we are considering at least 2 state variables. So we have considered the state space variable of x1, x2, x3. As you see that the equations of both unsprung and unsprung mass. This is the x of x, ZS meant ZU and Z2. Accordingly, by the derivation of Z1, Z2, Z3, we get Z1 dot, Z2 dot. From this equation, we will get Zx dot and Z double dot.
Hello guys, I am Padmanabh, and now I will continue the presentation with the Laplace transformation. So basically, the Laplace transformation technique provides a useful and simple method to evaluate the performance of controlled system. This integral transform is used to simplify the solution of linear equations by converting the differential equation into algebraic equation. Now, taking Laplace transform of equations of motion 3 and 4, these two equations we get. In this, mu is the unsprung mass, kp is the tire stiffness, ms is the sprung mass, bs is the damping coefficient, and ks is spring stiffness. So now we'll solve these two equations. So now simplifying the above equations, we get this. Now converting these equation 5 and 6 into matrix form, we'll get the following equation. Now, as the value of unsprung mass is very less compared to the sprung mass, for the simplicity we can eliminate the value of x1 equation, where delta is the denominator and is defined by the following equation. You can see that delta is okay. So finally, the final equation we'll get as Laplace transform of the output divided by Laplace transform of the input is equal to the following equation. So this is nothing but the transfer function of the quarter car passive suspension system. Next is the conclusion. From the state space modeling, matrix formation was carried out, and the formation of matrices by taking Laplace transform, the transfer function of the system was carried out. Quarter car automotive suspension model is one of the best and simplest ways for analysis of vehicle ride or comfort with 2 degrees of freedom system. As in case of quarter car suspension, sprung mass acceleration is used to quantify the ride quality. Sprung mass acceleration can be obtained by substituting values of sprung mass, unsprung mass, damping coefficient, and stiffness values of tire and suspension in the transfer function. Okay, thank you.